So for excavations, we have, I would say, 3 programs, or 3 programs can be used. It's sheeting design, sheeting check, and of course you can use finite element program. Sheeting design was made for designing of, fast designing of, especially non-anchored wall. For non-anchored wall, it's absolutely great and fast. If you have some anchoring system, it's good for designing the measurements and dimensions of the bar sheeting. So you measure how deep you have to go, you compute how deep you have to go to the soil. Sheeting check is, I would say, the best program for calculating any type of reinforced wall or sheeting pile or raised sheeting pile for any type of construction. It can be used for real modeling of real behavioral structure. I will show you how it works. It's more complicated than sheeting design, but still very user-friendly. The most difficult, I would say, modeling of excavation is with finite elements. It's similar to Plaxis or to Midas when you use our finite elements. It can give you again nice results, some more information, for example the formation of the terrain behind the structure, but it's much more, I would say, much more difficult to make a good model because you have to introduce some contact elements and so on, etc., etc. I will show you. So in the beginning I will start with sheeting design. So let's say that we want to design by sheeting, I don't know, 3 meters high. So we start with some geology. I'm not going to input again, so I can take the one that we use in the wall, paste it, and here I can, copy data, and here I have to paste data. And you see I have the same data we did in gravity wall. I have to input some geometry, so I thought, 3 meters, I'm lucky. Let's work. You can define type of construction, so it can be from steel, it can be from reinforced concrete, it can be from timber piles. So I would say most common sheet piles are here. You can use catalog. We have a lot of different catalogs of sheet piles that are, I would say, manufacturing in the world. So if you find that you are using or doing some different one, it's absolutely no problem, send it to us. We will implement to the software and you can use it. If you have something really special, you can input any type of construction just by, I would say, properties as area, moment on inertia, and the modulus of elasticity. You input it and you can compute. So I choose some typical sheeting, and I would say soils, water, and other we already inputted. So I can skip it and go to analysis. And you see that the program has calculated the minimum length of the structure into the soil, can calculate the bending moment and shear force on the structure. Then you can go directly to dimensioning, where we check the cross-section of the sheet pile. It's new, this function is new in version 2017. So if you had older version of GEO5, it wasn't there, it was only in cheating check. So here you can see some check of the steel cross-section according to the 3. And then you can go again to slope stability. You should define a real depth or real dimension of structure, because usually you design it a bit more, not 3.58. I would say that they would kill you on this construction site if you come with such a project. So you tell, for example, 4, and you can go to slope stability and again make some analyses, and you can see that looks good, so it is satisfactory. And I would say that non-anchored pile sheeting is designed. So it was really fast, safe, and no problem with that. If you have some anchor, it starts to be more complicated. I add some more. Oops. 1 meter, 3 meters. 6 meters, 2 meters. I put some slope, it's not very nice. So, if we input anchor, we could do the same analysis, but it wouldn't be correct, as if you have anchors, there's some redistribution of earth pressures. So behind the anchor wall or strut wall, there's not only active pressure, but there's some redistribution, so you can define it in a pressure determination. But we allowed, I would say, any type of earth pressure distribution that we found in the literature. So half is according American AASHTO standard, and half is about from German EAB, what they use. But the most simple way is, I would say, this type of redistribution, when the peak of the active pressure is at the same level as anchor. So you can choose this type, and the program is showing you what's happening, that you see active pressure that we computed, you see redistributed pressure, you see pressure from the water, and you see the total pressure acting on the structure. Then you can go again to analysis, and here we have more options. You can have a structure that is inked or fixed to the soil. So you can choose both type. So you know that your structure should be somewhere between 1.5 meters long in the soil, from 1.5 to about 3 meters. And it's up to you what you decide, because it will depend on the formation. If you have some restriction with the formation, and again, if you have longer sheet pile, you have, I would say, lower forces in the anchor. So you can choose something between. And then again, you can check dimensions of the cross section, and again stability. I'm not going to show you again, it's all the time the same. Maybe the anchor will be in the source stability. So it's sheeting design. It means that if you want to design non-anchored wall, pile wall, it's absolutely simplest and ideal program. If you have the wall that's anchored in one row, maybe 2 rows, you can use it. If you have really 10 meters excavation with anchors in 4 rows, okay, skip it and go directly to sheeting check. So, at the beginning, I will start with the program that I will show you how it works, and then I will show you some real project, what was done in sheet and check. In this program, you can compute any type of excavation. So, again, I paste data what we had before, but in this program we had to define the lengths of the structure. So we can say that we have, for example, 6 meter long wall, and again we can define what type of the wall we have. So we can have, for example, concrete pile, sheet pile, timber pile, ice section, and so on. All types of structure can be checked. So to the piles you can put reinforcement and check if the cross section with reinforcement is okay. So let's make a pile wall, and here you have to model the construction step by step, the same way as you are doing on the construction site. So it's important to know when you start to dig, when you introduce anchor, to what force you prop the anchor. So I show you how it works. So in the beginning, we make some small excavation. About 1 meter. And go to analysis. So we see the deformation of the structure. The deformation is red, and here you see the pressures that's acting on the structure. So the green, the first one is active pressure, the second one is pressure at rest, and the third one is passive pressure. And pressure that's acting on the structure depends on its deformation. So it means that if you have a high deformation, there's on the right you have active pressure, it's over here, and on the left you have a pressure that can be passive. I make, I would say, better example. that it will be more visible for you. Sign. The deformation looks a bit better, but more excavation. You see that the deformation, what I don't like, that I wanted to show you some nice deformation, and this pile wall that I did, about 1 meter thick piles, are very, very stiff, so there's no deformation. So I change it, and you will see the result. Then from the very thick piles, I change to not 1 meter piles, but I change to, for example, some small sheet pile. And you see that the deformation is completely different because the structure is not so stiff. And in the sheeting check, we calculate with the stiffness of soil, that is modeled by modulus of subgrade reaction, and of course with the stiffness of the construction. And the stiffness has a high influence to the result. In sheeting design, it's not important what type of structure you have, but in sheeting check, I would say all stiffness and all material properties are important for the results. So here you can see a typical sheeting with deformation to the excavation. Here on the right side we reach active pressure, and here the pressure is I would say higher than pressure at rest, but not so much because passive pressure here is pretty high. So we have a first stage of construction, and then we can introduce another construction stage and say, now we input some anchor. And you have to input the stressing force. In version 2017, we have a new possibility to define what type of anchor you have. So you can have stress bars and anchors and helical anchors and deadmans and so on. And we can use again the catalog or database of different anchors. So you don't need to input all material properties of the anchor. And you can even check if the anchor is sufficient for pull-out resistance, for tensile strength, and for the, I would say, root or cement of the root. So I like this one. Let us strength anchor. So you see the shape of the anchor that I input. I make a higher excavation. For example, centimeter, and go again to analysis. And you see what happened. I put rather high force to the anchor, so construction was deformed a bit back to the soil. The pressure on the right is near passive pressure, and we have such a shape of deformation. Again, we can introduce some other construction stage, and we can make other excavation. I will make rather high excavation, so you see what happens if the construction is not stable. I do the analysis, and you see that program didn't find any solution. It's just because here on the right side we reach active pressure and here passive pressure. So it means that the structure would collapse. So it means that we cannot do such a big excavation, or we have to introduce another row of anchors. So I will go back. Excavation is here. I'm sorry, I didn't took my glasses. So take just only 4 meters. I can introduce another row of anchors. 2.5 meters. Analysis. And again, I can add another construction stage and my final excavation to that 4.5 meter. So you see that you have to model the construction as the same way as you build it, as you are building it on the side. Because if you start with the anchor and then make excavation, you have it's different result than if you make excavation first and then you introduce anchor. Because anchor, prop or support is put on already deformed construction. It's not, I would say, elastic or linear analysis, but it takes into account all deformations, and you have to go step by step. And you see the deformations of construction, then you can check internal stability of anchors, if it is okay or not. You see that I didn't make design very nice, so the upper row of the anchors are not sufficient. Again, you can check slope stability. And you can check the cross section what we did. So for the steel, I showed you. If we change to, in the beginning, say no, I don't want to have it from steel, I still insist on that complete profile. I just make it smaller. The advantage is if you click something really wrong, as I did it now, you immediately see it. So something like this. You can go to analysis and you can compute all stages that we did. You see that now deformation is completely different because we have a different stiffness of the pile. Go to dimensioning, and now we can make check of the reinforcement of the sheeting check. So the way how the program sheeting check works, so it gives you, I would say, any information you need about this type of construction. So, for example, here you can see a real construction. It's from underground in Czech Republic in Prozac station. It was a temporary sheeting when they built the station, and you see how it is modeled. The geometry was 21 meter high. So there was a lot of construction stages. So they start with some excavations in meters, and when you click on this example, you can see how it is modeled step by step. All the time they put new anchor, do some excavation, put new anchor. If you look at the results of deformation, you see that in the beginning there was some deformation of the wall. It was base sheeting, so it was done by steel profile with wooden, with horizontal wooden facing between the king piles. So you see that when we introduced the anchor, the deformation went back to the soil, but only a bit, not so much, not the direction of the deformation didn't change. And you see step by step how it changed and what deformation has developed. At the same time, there's a check of all other situation or limit cases. This example that I'm showing you, you can find in engineering manuals, and we have it even in Project Gallery. Maybe you received this paper. I'm not sure, maybe not. I can show you on our web, because on this structure there was done inclinometric measurement, so we know the results, how it behaves on it, and I have to say that the prediction from the program was very, very good, and you can see it in these materials. So I will try to find it. nevíš to je.
Možná research papers.
Není.
To nevím. Můžeme to najít z přestávku a potom to ještě.
Reflex.
Jo? Jo.
So you can download it. I suppose we have it in English, maybe in Russian too.
Jestli asi jenom stáhli, bude to otevřít.
Yeah.
Tak.
So here you can see that wall that I was talking about. This is the construction pages, and here's the table of measured displacement and the displacement that was calculated by the program. So I believe that this program can give a really very good result. Comparing with finite elements, the main advantage of this program is that you are inputting just multiple parameters, angle of friction and cohesion, and earth pressures is one of the, I would say, tasks that geotechnical engineers can do. We know the pressures. So I would say that this is the reason why this can give you very realistic results and realistic predictions of behavior of the structure. Of course, the problem is the magnitude of deformations, where the input of subgrade, modulus of subgrade reaction is, I would say, rather complicated, and it's all the time the question what to use. Modulus of subgrade reaction is defined here. And we have many methods of determining of this modulus of subgrade reaction. We have our own method that was developed in Czech that we calculated from ediometric modulus of soil. We recommend to use Schmidt theory that is well accepted around the world and again give rather good results. But you can use any different way. For example, in Italy, they use dilatometer. So you can input just measurement from dilatometer and compute subgrade modulus from that. In French, they use pressure meter. In Dutch, they have another, I would say, special material how to compute it. And all this is implemented in the programs, in the settings, but normal. I can show you here, you can choose. You can choose different ways how to compute that subgrade reaction modulus, but usually with a Schmidt or with an iteration process of subgrade reaction, you receive nice results. But again, this program is much more complicated, the sheeting design. You have to know something about the model. You have to understand what soil properties to input and how to work with it. Again, it's still less complicated than finite element method.